invariant reductions. Kostya, you are welcome.
Oh, yes. Thank you. Thank you. Thank you for having me. It's a big pleasure to present our results here. And this is a joint result, joint with Alexei Shirikov. Yes, this talk continues the previous one, devoted to the invariant reduction of conservation laws for 1+1 evolution systems. And this talk is devoted to the general mechanism of the invariant reduction. Yes, so in a nutshell, we will consider a system of PDEs and their evolutionary symmetries. More precisely, we will consider their invariant solutions, systems that describe invariant solutions. And when it comes to exact solutions, the method of constructing of exact solutions, the most interesting method or the most famous method is the Lie method related to invariant solutions, right? We have a symmetry, we can consider the corresponding invariant solutions. But it turns out that we can do actually more than just consider systems for invariant solutions and try to solve them directly. Systems for invariant solutions inherit invariant geometric structures in a very natural way. Maybe not all of them, but the most interesting ones, at least. And this mechanism of inheritance is not the most obvious one, because when we talk about reductions, we talk about subsystems of our original systems. Since they are subsystems, we have the corresponding embeddings. We can use the arising pullbacks. We can pull back, say, Vinogradov spectral sequence. And of course, any reduction inherits geometric structures, but it inherits in the direct way. We will discuss a bit more tricky inheritance mechanism when we reduce something like horizontal cohomology degree. Let's consider system of PDEs given by formula 1, and its evolutionary symmetry. We can consider the corresponding system that describes invariant solutions, and the system is given by formula 3. So instead of the original system, we can consider the original system plus equations of the form the characteristic on the left-hand side equals to 0 on the right-hand side. If we equate the characteristic to 0, we get the corresponding invariant solutions. On this subsystem epsilon x, the symmetry, the evolutionary symmetry x vanishes. So all points of the system epsilon x are the subsystem epsilon x describes the corresponding invariant solutions. And the reduction mechanism is based on the following simple observation that the evolutionary field vanishes on this system epsilon x. Actually, this condition is just precisely the condition that we deal with invariant solutions. But this implies that the Lie derivative operator also vanishes on the invariant subsystem. That is why we can reduce something like horizontal degree by 1, and this reduction mechanism is given by the formula 5. When we deal with a representative of an invariant structure, an invariant cohomology element, so omega here represents an invariant cohomology element, and the words that this cohomology element is invariant, generally speaking, they mean that the Lie derivative of this representative must represent a trivial cohomology element. So on the left-hand side here we have this Lie derivative, and on the right-hand side we have some coboundary. But one can see that if we restrict this formula, so this formula just expresses the idea, precisely expresses the idea that the cohomology element is invariant, nothing else. But one can see that we can actually restrict this formula to the subsystem epsilon x, and on the left-hand side we get 0 because the Lie derivative vanishes. On the right-hand side we get the arising cocycle, right, for the invariant subsystem. And this cocycle has a different cohomological degree or horizontal degree or something like horizontal degree at least. So the mechanism reduces its degree by 1. This is our story in a nutshell. But now let me be more specific. So first of all, I have to introduce some notation and some discuss some ideas, some basic ideas, basic constructions. So let me begin with jets. Suppose that we have a locally trivial smooth vector bundle pi. We have n plus m dimensional base E and n plus m dimensional total space E and n dimensional base M. Both of them are smooth manifolds, and it's a locally trivial smooth vector bundle. Denote by x, x1, etc., xn coordinates in some coordinate neighborhood such that the bundle becomes trivial over it. x1, etc., xn are independent variables. Also denote by u1, etc., um coordinates along the fibers of this projection over u. They are dependent variables. Denote by ui alpha adapted coordinates along the fibers of the corresponding projection from the infinite jet manifold to the base over u. Yes, here alpha is a multi-index, and we consider multi-index as a formal sum of this form, alpha 1 x1 plus etc. plus alpha n of n. It's convenient to introduce a multi-index in this form. Maybe it would be better to introduce multi-index in the form of like exponents using powers like x1 to power alpha 1, etc. But since they are lower indices in formulas, this notation would be cumbersome. We don't want to use such notation. So this is why I use notation of this formal sum. So multi-index is formally considered as a linear combination with integer, non-zero integer, I mean, non-negative zero or non-negative integer coefficients. And modulo alpha means the sum of the coefficients. Besides, we have the following natural projections given under Formula 6, or not given, but just denoted under Formula 6. We have projections from the infinite jet to finite jet manifolds, and from finite jets to the base of our original bundle. And using them, we can define functions and differential forms on the infinite jets. So here, functions and differential forms are just, roughly speaking, they are objects that come from finite ordered jets, right? So our functions on the infinite jets is just the union of all smooth functions on finite ordered jets. So we do not turn this algebra into sheaf, or more precisely, we don't consider this algebra, in principle, this algebra generates a sheaf, but its global sections, the algebra of global sections is not isomorphic to the original one. So we deal with the filtered algebra here instead. And also we define differential forms in the same way, in a similar way, at least. So all differential forms are also coming from finite ordered jets. The main structure on the infinite jet bundle or on the infinite jet manifold is the corresponding Cartan distribution. And using adapted local coordinates, we can describe the Cartan distribution in terms of total derivatives, dxk. The corresponding total derivative is given in adapted coordinates. And such total derivatives span the corresponding distribution, the Cartan distribution. At each point, they span the plane, the respective plane of the Cartan distribution on the infinite jets. We can dualize this point of view. We can consider the corresponding ideal of Cartan or contact forms in the algebra of differential forms in the exterior algebra. And Cartan forms are generated by homogeneous forms that vanish on the Cartan planes, because differential forms, we can consider them functions of tangent vectors. Say, if we fix a point, then the differential form at a point becomes a function of tangent vectors. We can restrict this function to the Cartan plane, and if this function vanishes at each point, then the corresponding form, differential form, is a Cartan form or contact form. Speaking of Cartan 1 forms in coordinates, they have the form 10. Theta I alpha denotes the basis forms. Yes, the basis contact forms, and any other Cartan form, one form, locally has the form omega alpha I, theta I alpha. It's a finite sum. It must be a finite sum, and omega alpha I are functions of adapted local coordinates. They also must depend on a finite number of arguments and more than that, but let's move further. So there are functions of local coordinates. Using Cartan forms, we can introduce horizontal forms, which are basically just differential forms modulo Cartan forms, and we can identify horizontal forms with the model on the right-hand side. So we just take forms from the base, pull them back to the infinite jets, and consider them with coefficients from the algebra smooth functions. This identification is possible because we have this bundle structure on the infinite jets. So we use this bundle structure. Instead of equivalence classes of horizontal forms, we can consider their representatives. So each element from here represents a horizontal form, and each horizontal form is represented by a unique element of this module. So we can identify horizontal forms with their representatives. This allows us to introduce horizontal differential. We will consider it in terms of representatives mostly, but of course it exists without any identifications and so on. Yes, and it's important to know that we can interpret horizontal n forms as Lagrangians. Moreover, we can consider the corresponding horizontal cohomology using the horizontal differential. And the horizontal cohomology class of a Lagrangian is simply the Lagrangian itself plus th of the horizontal n-1 forms. Yeah, let me now talk about equations. Let zeta be a locally trivial smooth vector bundle over the same base M. A section of the induced bundle of this form. So we just induce the corresponding from the bundle zeta. We induce the bundle using the projection from finite order jets to the base M. And a section of this induced bundle defines the corresponding differential equation given by the formula 14. F equals to 0, or in local coordinates, Fi, where Fi denotes components of this section F. Fi of x and u alpha equal to 0, where alpha, the model of alpha, cannot be greater than R, since we use the projection PR. So it's R's order jets. They describe R's order derivatives, roughly speaking, in coordinates. The infinite prolongation of this system of equations, or of this equation, is the system given under the formula 15. So we just take left-hand sides, we take all their total derivatives, that is differential consequences, and we get the corresponding infinite system of relations, infinite system of equations. And this system describes a subset of the infinite jets. And this subset admits simple interpretations, just the set of formal solutions of the original system. So instead of solutions, we consider formal solutions, that is Taylor series. Or speaking more geometrically, Taylor series become infinite jets. So we consider infinite jets, or in other words, in local coordinates, we can say that we consider Taylor series that satisfy to the original system of equation, or to the original system of equations considered together with all its differential consequences. Yes, and this system is endowed with its own Cartan distribution C, and with the corresponding algebra of smooth functions, which is basically just the restriction of the algebra of smooth functions from infinite jets to the system epsilon. Besides, we describe the corresponding differential forms on epsilon, and they coincide with the restriction of the algebra of differential forms from jets to epsilon. And in a similar way, we can describe the corresponding Cartan forms. And using the Cartan forms, we also can describe sections of the Cartan distribution understood as a subbundle of its tangent bundle, of the tangent bundle of the equation epsilon. So using the Cartan forms, we can describe Cartan vector fields, for example. Yes, I assume some regularity conditions, some natural regularity conditions. Namely, I assume that the projection from the infinite jets to M, the base M, restricted to our system epsilon, must be surjective. So the projection must give M itself. This simply means that we don't want to face relations between independent variables only. Since we deal with differential equations, we don't want to face relations with, between independent variables only. Besides, I require that the differentials of these components in local coordinates are independent for any point such that at this point f is 0, any point rho such that at this point f is 0. So at any point of this surface, f equals to 0 describes the surface, and I simply want to know that the section f itself is regular, and that the equation without infinite prolongation, the original equation, is just an embedded submanifold of the corresponding finite order jets, of R's order jets. This requirement may be not that important. We can consider not that restrictive requirement, but the condition itself is not restrictive eventually. And I just like to know that I have a submanifold and the section is regular and all of that. That is why I use this requirement. Yeah, the third one is more important. The third one is actually the regularity condition itself. We require that the function vanishes on our equation manifold if and only if it can be represented in the following form as delta of f for some total differential operator. Total differential operator means that the differential operator, like in total derivatives, so in components, this operator has this form. Of course, there are some requirements on its components. There are functions of local coordinates, but they must be functions that can depend only on derivatives up to some finite order, the same for all adapted coordinate systems. So this is the main regularity conditions actually for us. And besides, we have the fourth regularity condition, which means that the Rampe homology groups of our epsilon must be trivial for I greater than 0. This regularity condition is not that important. I mean, it's not important at all. But this condition just simplifies some formulas. And it's nice to have this condition because when we describe objects, geometric objects in terms of operators, say when we describe conservation laws in terms of their cosymmetries and all of that, the description relates non-topological objects and the corresponding operators, cosymmetries, or something like that. So if you want to control these geometric objects in terms of their like characteristics, say characteristic operators, we want to deal with non-topological objects only in this case. And that is why the topology of epsilon must be pretty nice. I mean, I require it, but without this requirement, everything works still perfectly. It becomes a bit more complicated to know that the object is trivial, like is not a topological object, because it can be important during our discussion that the object is non-topological. So it's a topological conservation law, say, can be non-trivial eventually, in our sense. It can cause problems. But let's discuss symmetries. Symmetries of infinite jets are just elements of the following module of characteristics given by formula 17. So we just simply take pullbacks of sections of finite, using finite order projections from finite order jets to the base, and consider their sections and consider their union. Of course, this notation is a bit informal. More formally, we can discuss something like direct limits, or we can describe how we can interpret such sections of finite order pullbacks in terms of sections over the infinite jets and so on, but I hope that it's more or less clear what it means. So basically, characteristics of symmetries are just sections of some finite order pullbacks. And in coordinates, if we have a characteristic, then it is given by like vector function with components phi1, etc., phi-m. These components depend on independent variables, dependent variables, and derivatives up to some finite order. The same for all adapted local coordinate systems. And such characteristics describe the respective evolutionary vector fields, also given under formula 18. So basically, symmetries of infinite jets are vector fields of this form, but we can identify them with their characteristics. And when it comes to differential equations, the description changes. Namely, a symmetry of epsilon is a derivation of the corresponding algebra that preserves the Cartan distribution in the sense given under the formula 19. So the derivative must preserve the module of Cartan one forms, where by the derivative we mean the magic Cartan formula. We do not assume any filtration on this algebra. So we do not assume that a derivation must respect any filtration in this sense. And trivial symmetries of epsilon are sections of the corresponding Cartan distribution. That is, we can understand the Cartan distribution as a subbundle of tangent bundle, and then we can consider the corresponding sections. So the trivial symmetries are derivations of this form, and we consider symmetries as equivalence classes eventually. So a symmetry is an equivalence class where two symmetries are equivalent if they differ by a trivial symmetry. The restriction of an evolutionary field is a symmetry of epsilon if and only if the formula 21 holds. That is, if and only if the result of the application of this evolutionary vector field to the left-hand side of our system vanishes from the infinitely prolonged system. Yeah, and it's important to know that if our projection from the set of formal solutions to the zero-ordered jets is surjective, then any symmetry is equivalent to some evolutionary vector field restricted to epsilon, or in other words, it is equivalent to the restriction of its characteristic to epsilon. So all symmetries, in essence, all symmetries are evolutionary symmetries in this case. And it's also interesting that in literature, usually this theorem is given in terms of vector fields that respect a filtration of the algebra of smooth functions, but we do not consider any filtrations. And the filtrations are not important in this case, actually, because it's easy to see that zeros jets are just E, so it's a smooth manifold. And we know that the module of differential one forms on a smooth manifold is generated by a finite number of functions, by a finite number of their differentials. So anyway, any derivation of this algebra maps the algebra of smooth functions on this smooth manifold into some finite degree subalgebra of our algebra. So this property still holds even if we do not consider derivation that respect a filtration in any sense. Yeah, the most important ingredient of the story is the Vinogradov C-spectral sequence. This C-spectral sequence controls geometry of a differential equation in some sense. And we have the property 22, since the Cartan distribution is involutive, and it is involutive. So since it is involutive, the corresponding ideal of Cartan forms is differentially closed. But we also can consider its exterior powers. So Cp lambda means P's power of the Cartan ideal, the ideal of Cartan or contact forms. And such powers are also differentially closed. That is why we can consider the arising filtration of the DRAM, of the complex of DRAM, of the DRAM complex. And lambda bullet means the DRAM complex. So this filtration gives rise to, oh, wait, it's the wrong sign, wrong direction. This filtration simply generates the Vinogradov spectral sequence. And as usual, we have the corresponding differentials of this spectral sequence. All of them are induced by the drum differential. On the zero page, we have the corresponding modules of over our algebra of smooth functions. And EPQ means simply P times Cartan form, at least P times Cartan form, at least P times degenerate, because Cartan forms are forms that degenerate on solutions. So roughly speaking, I mean, we can use this terminology that such forms are at least P times degenerate on solutions, modular forms that are at least P plus 1 times degenerate on solutions. Or vertical forms or contact forms, at least P times contact form, modular at least P plus 1 times contact forms. The corresponding group on the first page is described as usual as the kernel of the operator modular the image of the previous operator. And using the bundle structure, we can identify the zero page or group or elements of a group on the zero page with forms that are precisely p times Cartan forms and q times horizontal forms using the bundle structure. Actually, this bundle structure is not that important for us today, but it simplifies the description. From what I understand, the basic role of this bundle structure is usually to simplify the description, but there is a chance that it may hide something because the bundle structure, the description in terms of bundle structure changes something and may hide some information. And we will see an example of this situation today. So it's a nice thing, in terms of simplifications, but also it can hide some information from us. It makes something obvious less clear, let's say. Using this identification, we can describe the differential d0 in the following simple form, and we can also introduce the vertical differential, which is the difference between the theorem differential and the d0. Today, I don't need this vertical differential because I omit a lot of proofs in this talk. But in principle, in the proof, it's convenient to use the vertical differential. We can describe everything without it, without bundle structure, but it's convenient to use it. Yeah, and the variational k forms of epsilon are elements of k n minus 1 groups of the Vinogradov C-spectral sequence on the first page. Here, n minus 1 basically means that, roughly speaking, we treat time as something one-dimensional. So n minus 1 is the dimension of space. And in this sense, conservation laws are variational zero forms. We can integrate something. We can take an instantaneous state described by n minus 1 closed submanifold. Closed means compact and without boundary. And we can integrate such elements over such submanifolds over instantaneous states. So conservation laws are functions of instantaneous states, roughly speaking. And then presymplectic structures are two forms, and their description in terms of instantaneous states gives us variational two forms. And we also require that they must be declosed, D1 closed. That is, they are variationally closed, variational two forms. Yeah, so now let me describe the reduction mechanism itself. This is the main part of my talk. So let X be a symmetry of the infinite prolongation of a system of differential equations f equals to 0. Then we have the formula 26, because the evolutionary vector field in adapted coordinates is given by this combination, by this formula. Then X invariant solutions satisfy the invariant subsystem epsilon x, given under the formula 27. So we consider that the infinite prolongation of the original equation plus of the equation, the characteristic equals to 0. Suppose that omega represents an X invariant element of a group on the first page, of a group on the first page of the Vinogradov C-spectral sequence. Since it is invariant, the derivative of the representative must represent a trivial element. That is, it must be a coboundary. So there must be an element theta such that the derivative is d0 of this theta. Then the restriction of the theta represents an element of a group on the first page of the Vinogradov spectral sequence for the invariant subsystem. Because if we restrict the left-hand side, the subsystem, we get 0. So restricting the right-hand side, we get the formula 29. And this formula is the reduction mechanism itself. If we take an X invariant element on the first page of the Vinogradov spectral sequence for the original equation, it generates an element on the first page of the Vinogradov spectral sequence for the invariant subsystem, but its horizontal degree is reduced by 1. So it reduces the horizontal degree by 1. In this case, we can say horizontal degree in terms of this spectral sequence without any like quotes and quotes. So in terms of the Vinogradov spectral sequence, the reduction mechanism reduces the horizontal degree by 1 precisely. So it's a different reduction mechanism. I mean, relative to the standard one, when we just pull Vinogradov spectral sequence pull back using the embedding, using this embedding of the subsystem into the system, because this pullback doesn't reduce any degree, and this reduction mechanism reduces the horizontal degree by 1. And the reduction is defined up to the restriction of the corresponding term on the Vinogradov spectral sequence. Since we have the formula 30, if I take a different representative of the same cohomology element, then I have something that lies in the image of this differential here, but the Lie derivative and the differential d0, they commute. So I can switch their positions and get something like that instead. But the image of the Lie derivative vanishes on the invariant subsystem as the Lie derivative vanishes on the invariant subsystem, because the vector field itself, the vector field x, vanishes on the invariant subsystem. So using this formula, we can see that the only problem may be caused by the kernel of this operator, of the differential d0. That is why the reduction is defined up to the restriction of this group to the subsystem. And here, I mean the restriction in terms of the pullback of this inclusion, this embedding. So we can see that if this restriction is trivial, or for example, if the group itself is trivial without any restrictions, then the reduction is, it can be interpreted as the homomorphism from invariant, yes, and this description is a bit incorrect. So here we have something like X invariant part of this group, and here we have this group, yes, this group is okay. So the reduction mechanism is homomorphism. Let's consider an example first. Let's consider a Lodger-Bogoliansky sheaf-breaking soliton equation, which is given under the formula 32. This equation is a very interesting equation. First of all, it's 1 plus 2 dimensional equation, but it turns out that this Lagrangian equation actually admits an infinite hierarchy of higher symmetries. This is a beautiful result given by Josip Krasishik and Oleg Morozov. Very nice equation with higher symmetries, which is 1 plus 2 equation, not 1 plus 1. So let's consider one of its higher symmetries. Let's take the symmetry phi given by the formula 33. And let's take its X invariant conservation laws represented by differential forms omega 1 and omega 2 under the formula 34 and 35. So let's take these conservation laws. Directly solving the arising equations on the equation epsilon, we obtain, for example, the following potentials. Of course, there are other potentials given by the differential of functions, d0 of functions on epsilon. But we can take these potentials, and they are actually 2-component horizontal one-forms. Not 3-component, but 2-component horizontal one-forms, which is interesting in itself. Yeah, but let me note also that everything happens on epsilon, not on gx, not on epsilon x. So the reduction mechanism is basically described on epsilon, on the original system of equations, because the potential lives on the original system. So we get these 2 potentials, and we can restrict them to the arising invariant subsystem. The invariant subsystem is given by the original equation plus the equation which has the form like the characteristic equals to 0. Of course, we consider the infinitely prolonged system. And the main result is that the reductions of the 2 conservation laws are represented by the 1-component horizontal one-form. So they become not 2-component, but even 1-component horizontal one-forms after the restriction, theta 1 and theta 2 restricted. And both of them have this form like g multiplied by something, and g is this function. One can see that this actually means that g is a constant of invariant motion. That is, for any solution, invariant solution of the original equation, say with a connected domain, this function g restricted to the solution is a constant, just a real number. So it's a constant of invariant motion. This means that the system is not differentially connected. The system becomes not differentially connected because of the structure of conservation laws. But G cannot be obtained through the invariant reduction mechanism directly. We obtain it we get it using these one forms, right? The reduction of conservation laws. And they are given by equivalence classes of one forms. But we cannot actually obtain G directly using the invariant reduction mechanism because the corresponding group of the Vinogradov C-spectral sequence of the original equation of CBS itself is trivial. The group which could generate something like some element which can be reduced to G. So this G is not inherited from the original equation. This G was born precisely here on this subsystem. So this G exists only when it comes to invariant solutions. Yes, and it's important to note that when we consider reductions in this form, when we do not exclude any independent variables and just consider systems, overdetermined systems of this form, it becomes not that easy to establish the non-triviality of the arising objects, of the reductions. One nice idea is to use compatibility complexes, but the problem with that, in this case, for example, the compatibility complex must be pretty long. Its length is not 3, it is at least 4, because the system is not differentially connected. So it's not that easy to construct the compatibility complex in this case. And besides, we have a lot of differential consequences of this equation of orders less than 4 or equal to 4. So this problem becomes challenging, to construct the compatibility complex. From what I understand, it is challenging to me, because I don't know how to do it in a reasonable way in this case. So it's not always possible to use, maybe it's not always possible to use compatibility complex to to establish non-triviality of some elements. And even in this case, if I want to establish their non-triviality of these reductions, I must demonstrate that they do not lie in the image of some differential operator, again, because the length of the compatibility complex is at least 4. Their non-triviality in terms of compatibility complex, in terms of K-line theorem, means that they must not lie in the image of some differential operator. But it's not that easy sometimes to establish that something is not in the image of the differential operator, right? Because basically this is the same problem. If we do not use compatibility complexes, we can try to demonstrate that they are not in the image of the differential D0. So basically it's the same problem. This is about some challenges regarding the non-triviality of the reductions. But now let me discuss some theorems that relate Vinogradov spectral sequence of the original system and of the reduction of the invariant subsystem. So theorem 1, let epsilon be an infinitely prolonged system of differential equations and let X be its evolutionary symmetry. Suppose that we have this situation when these groups are trivial, then on the X invariant subspace of this group, on the X invariant subspace, not on the entire group, we have this formula. So basically we have the relation between D1 on the epsilon and D1 on the invariant subsystem in terms of the reduction. And we have this minus, and this minus is important actually. It appears, it arises from the analog of bicomplex. We can consider something like bicomplex, variation of bicomplex here, and the minus arises from it. So they are related, but through this minus. And theorem 2 is more or less the same theorem. It describes the same effect. Suppose that X and X1 are commuting symmetries of an infinitely prolonged system, epsilon, commuting evolutionary symmetries. If we also have some technical requirements, then on the X invariant subspace of this group, we have the relation between contractions. We can contract elements with X1 on epsilon, and then reduce them, or we can at first reduce an element and then contract it with the restriction of X1. And again, the results are almost the same, they differ in sign eventually. And this sign arises for the same reason as this sign. Okay, now let me go to the internal Lagrangian formulas, because we can describe the reduction not only of Vinogradov C-spectral sequence elements, but also of some other elements, because the reduction mechanism is cohomological in itself. We can describe reduction to cohomologies. Well, denote by E tilde 0 k minus 1 1 the cohomology group of this complex at the term lambda k over C2 lambda k. Yes, here, let me note that here the total degree is k minus 1, while representatives of this element are given by k forms. So roughly speaking, tilde means +1 in terms of form degree. Tilde is +1 in terms of form degree. K minus 1 can be interpreted as the dimension of instantaneous states described by this group. So when we deal with internal Lagrangians are elements of this group, and n minus 1 denotes the dimension of instantaneous states. And here we have 0 because this index must describe an additional dimension, but the additional dimension is not specified. It can be anything. It can be given by a Cartan vector at the corresponding point, or by a vertical vector, or by their combination, and so on. So this dimension is not specified. That is why this tilde means +1 in terms of form dimension. Yeah, and we have the following Noether formula, which allows us to get elements of this group from Lagrangians admitted by the system under consideration. So the Noether formula basically tells us that for any Lagrangian, there is the corresponding presymplectic potential or presymplectic potential current that is 1 times vertical and minus 1 times horizontal form on jets. This formula is on jets, such that we have this formula. In other words, this formula is also the green identity or the Noether formula. This is the original formula from the Noether paper, roughly speaking. On the left-hand side, we have this derivative with respect to a parameter. So if we use integrals, then this is just the variation. This term describes the variation of the Lagrangian. And on the right-hand side, we have the corresponding integration by parts. E of L is the Euler operator. E of L equals to 0 describes the corresponding Euler-Lagrange equations. And here we have dH, horizontal differential, of some contraction of this form. If the variational derivative of a Lagrangian vanishes of our system epsilon, then this combination L plus omega L restricted to epsilon gives rise to a unique internal Lagrangian. This combination gives rise to unique internal Lagrangian. Besides, we have the corresponding differential from internal Lagrangians to variational to forms, and actually this differential maps internal Lagrangians to D1 closed variational to forms, that is to presymplectic structures. Each internal Lagrangian gives rise to a presymplectic structure. So to sum it up, we can say that the horizontal cohomology class of a Lagrangian such that its variational derivative vanishes on epsilon gives rise to unique internal Lagrangian of epsilon, which gives rise to a unique presymplectic structure, omega, an element of this kernel, that is to the variationally closed variational to form. Yes, and let L be a Lagrangian such that its variational derivative vanishes on epsilon, and let omega be the corresponding presymplectic structure. In this case, we have the Noether theorem, which tells us that if a variational field preserves the horizontal homology class of L, then there is a conservation law of our system, such that for this symmetry X, we have the Noether formula 45. So basically, the Noether theorem just describes the presymplectic structure and the relation between symmetries and conservation laws given by the presymplectic structure. But it also tells us how to figure out whether a symmetry generates a conservation law or not. And let me note that in this case, if we say, just for fun, take this formula and restrict it to the arising subsystem epsilon x, then on the left-hand side, we get 0, right? So on the right-hand side, we get d1 of the restriction is 0. And if the restriction is still a non-trivial conservation law of the reduced system, of the system epsilon x, then this restriction actually survives to the second page of the Vinogradov C-spectral sequence. And actually, there is an example, at least one. I know at least one example when this works in this way, when we restrict precisely this identity to an invariant subsystem, and we get a conservation law which survives to the second page. It remains non-trivial on the second page. So even in this case, even when we consider this, the restriction of such conservation law that correspond to the symmetries, to symmetries themselves, we not necessarily get zeros, restricting them to the invariant subsystems. Yes, for an invariant system epsilon x, we can replace omega with its reduction, if it's possible, and describe the same relation between symmetries of epsilon x, not necessarily restrictions of symmetries from epsilon, between just any symmetries of epsilon x, any noisy symmetries of epsilon x, and the corresponding conservation laws with reduced homological degree. So we can replace omega with its reduction, and this replacement expresses the Noether theorem for invariant solutions, or for systems that describe invariant solutions. Let me formulate some relation between the original Noether theorem and the Noether theorem for invariant solutions for L-normal systems. Let me introduce the linearization operator. We define LF of LF as an operator such that LF of phi equals to E phi of F. So phi are symmetries, roughly speaking. So this is like a differential of our section F, or of our equation F equals to 0, the original equation, because phi can be interpreted as symmetries of jets. Then epsilon is our normal if for the restriction of this linearization operator to the system epsilon, we have the following property, which tells us that if we have 0 of this form, if we have an operator that kills the linearization, then the operator must be 0. If a system has this property, then it is a normal. And for the normal theorems, we can formulate theorem 3 that actually relates the Noether theorem and the Noether theorem for invariant solutions. Suppose that we have two commuting symmetries, variational symmetries of an abnormal system epsilon, and let omega be an X-invariant presymplectic structure. And let Xi be conservation law such that X1 is a Noether symmetry, that is, it corresponds to conservation law, and in this case, it corresponds to the conservation law Xi. Then we get the formula 48. So this formula basically means that the relation given under the formula 45 remains the same when we restrict everything, when we reduce everything to the invariant subsystem. Because to reduce a symmetry to this subsystem is simply to restrict it, if it's possible. In the way when they are commute, there are no problems with such restrictions. So we reduce symmetries, we reduce presymplectic structures, and we reduce the corresponding conservation law. And the relation remains the same. So basically, the correspondence between the Noether correspondence between symmetries and conservation laws remains the same. But of course, on the invariant subsystem, we have more symmetries, more Noether symmetries in this sense, in the sense of this structure. In general, I mean, at least. And they can produce new analogs of conservation laws with the reduced horizontal degree. Yes, now let me discuss the same mechanism, but for PDEs without bundle structures. Let Y be a symmetry of epsilon, and let omega represent a Y invariant element of some group on the first page. Then there exists a potential of the same form, because this formula simply expresses the idea that the element represented by omega is Y invariant, if and only if. This is the definition of invariance. And then a reduction is represented by the well-defined restriction of this difference. It's important to note that this formula is not well-defined. This form is not well-defined. We cannot contract a symmetry and for an element on the zero page of some group on the zero page of Vinogradov spectral sequence. Because Y is some vector field, some symmetry, it's not vertical or something like that. Because we cannot discuss vertical symmetry since we do not have bundle structure in this case. And yet, the restriction of this counteraction is well defined because the system for invariant solutions is characterized by the condition that at its points, the vectors of Y lie in the respective Cartan planes. So when we restrict this combination to the system for invariant solutions, like epsilon Y, this vector field becomes just a Cartan vector field. And we can contract a Cartan vector field with an element on the zero page. So the restriction is well defined, but the object itself is not well defined, but it becomes well defined after the restriction. And this object is well defined without any restriction, but we still need to restrict the difference. Let me note that Jan Anderson and Mark Fels proposed a closely related reduction method, but still a different reduction method. For example, for elements of the kernel of D0 on epsilon arising from, and it's important, arising from the invariant part of the zero page on jets. So they consider it jets and zero page on jets. Besides, they consider some symmetries that generate flows, preserving the fiber bundle structure. That is, their reduction mechanism cannot be applied to higher symmetries in principle. They consider it symmetries that generate flows. But their reduction mechanism has an important feature. So basically, their reduction mechanism can be described in this form. If we have this formula, that is, omega is an invariant representative. It's more restrictive condition, right? So we have not just an invariant conservation law or something like that. We have an invariant representative in this case. But if we have an invariant representative, then using this observation given under the formula 50, we can see that, or under the formula 49, we can see that we can take theta y as 0, and then in the formula 50 we have only this term. Then we can take this term and restrict it to the subsystem epsilon x, epsilon y. It's not epsilon, it must be an epsilon y. So their reduction mechanism is mostly the same, but in their reduction mechanism we require that a representative must be y invariant itself. So their approach is less invariant because they consider symmetries generate flows, some of them, but their approach has a very interesting advantage. It's more or less clear how to generalize their approach when it comes to multi-reduction, right? We can see that like the basic idea is to consider like similar contractions, right? If we have, say, two-dimensional algebra, three-dimensional algebra symmetries, we can try to generalize the reduction mechanism in terms of contractions with something, at least with some like bivectors or something like that, multivectors. So on this naive level, it's clear how to generalize their reduction mechanism. While in terms of this reduction mechanism, it's not clear at all how to generalize it to the multi-reduction without like multi-reduction step by step, without restricting everything to the invariant subsystem, then taking the other symmetry and so on. Because here it's not clear how to reduce the horizontal degree of this guy by 2. For this term, it's clear. We can just contract with two vector fields. I mean, on a naive level. But for this term, it's not clear at all because this means that if I have two symmetries here, I must somehow to get something like roughly speaking, like double potential, something like that, with reduced degree by twice reduced degree. So it's not clear how to generalize the reduction mechanism to the multi-reduction because of this term. This means that we can only try to use solvable the algebras, and we can consider multi-reduction in terms of like step-by-step multi-reduction. But the situation becomes even worse, actually, with the multi-reduction in our mechanism, unfortunately. Namely, we have the following horrible situation. Let x and x1 be symmetries of an infinite parallel system epsilon, such that their commutator is proportional to x for some constant c, for some real number. So it's two-dimensional the algebra, solvable, of course. Suppose omega represents an element on the first page, that is both X invariant and X1 invariant. So it is invariant under the entire algebra. And we have, and suppose that we have also this technical requirement field. Let us denote the derivative, the potential by theta. Then we have the following property. If the reduction under the first symmetry is invariant under the reduction of the second symmetry and non-trivial, then C must be 0. They must commute. That is, X1 must be X invariant itself. If the result, if we can perform an additional step, this invariance and non-triviality means that we can perform an additional step of the reduction. If we can do it, then they must commute. Then they commute. And if they commute, then at least the reduction under the first step gives us an X1 invariant element of the corresponding invariant system. But the first property is the most horrible, of course, in this situation. So basically, it means that we cannot use solvable algebras. We have to use commutative algebras instead. At least when it comes to two-dimensional algebras. Yeah, let me sketch the proof. Let us denote by theta1 the corresponding potential for the Lie derivative with respect to x1. And hence we have the following formula. So d0 of c theta is the same thing as the Lie derivative along cx of our representative. But the cx is the commutator of x and x1. Then we have the Lie derivative along this commutator, but the Lie derivative along the commutator is the commutator of Lie derivatives. When we apply the Lie derivative with respect to x1 to omega, we get d0 of theta1 here, and we apply the Lie derivative with respect to x, then minus the same story about the second term. And eventually, since Lie derivative and d0 commute, we get d0 of something, right? So on the left-hand side, we have d0 of something. On the right-hand side, we have d0 of something. Since there are no homologies in this term, we get the following relation. The difference between the left-hand side and right-hand side must lie in the image of d0. Let us restrict the difference to the system epsilon x. Then we get the following situation. This term vanishes, and we have only two terms on the left-hand side. So c multiplied by the restriction of this theta, the epsilon x, and this term. And it's easy to see that if this element is x invariant, x1 invariant. If the restriction is x1 invariant, then this term also lies in the image of d0. So if it is x1 invariant, then if theta restricted to epsilon x is x1 invariant, then theta is trivial. If we want to have a non-trivial theta, c must be 0. Otherwise, we have a trivial reduction result. So if the algebra is not commutative, not abelian, then we get no reduction in this case, or at least we cannot perform the second step of the reduction. There is no chance to perform the second step. But to be honest, in the mechanism of Anderson and Fels, it was also clarified that in the two-dimensional case, for two-dimensional algebra, they also have some problem. They cannot also actually demonstrate something like multi-reduction for some deep reasons. So in two-dimensional case, it becomes really tricky, really challenging. And it's easy to see from the same formula that if c is 0, then the reduction is x1 invariant, right? If we don't have this term, then this guy lies in the image of d0. This means that the restriction of the reduction of the original omega to the system epsilon x is at least x1 invariant. And it's also important to know that the reduction of a conservation law, in the case c equals to 0, the reduction of a conservation law under x and under x1, then under x1, differs from its reduction under x1 and then under x in sign. And basically, this is what we would expect in this case, right? Because, like, comparing to the multi-reduction by Anderson and Fels, we see that they contract with some multivectors. So it's pretty natural to see that the reduction result differs in sign. In this case, in the case of commutative two-dimensional subalgebra. Yes, but now let us discuss a reduction of variational principles themselves. We can generalize our approach to the reduction of internal Lagrangians, and if omega represents an x-invariant element of such group, then we have the same formula, the same relation. This is just, again, the definition of invariance of the resulting element of the corresponding element on the first page, the element represented by omega. And we can do the same thing. It's easy to see that, to restrict this formula, and we see that the restriction of theta in this case, again, is a cocycle for the corresponding complex for the invariant subsystem. If k is n-1, that is when the dimension of space is n-1, then the reduction mechanism we get the reduction mechanism for X-invariant internal Lagrangians, right? Again, here we have not 0 pages, but first pages and X-invariant elements, not all of them. But for X-invariant elements, we get the corresponding reduction mechanism, and we get something like n-2 and tilde forms in this weird degree, in terms of this weird degree. And again, if we have this technical requirement field, then the reduction is well defined. At least for normal systems, this is always the case. The reduction is well defined, for example. Now let us consider variational principles determined by elements of this group. E0, 0, 0 here doesn't mean that they are 0 forms, because we have tilde, so they are 1 forms. They're represented by 1 forms, but the instantaneous states are 0 dimensional. So the instantaneous states are 0. This means that the space dimension is 0, so we have only time, roughly speaking. But we can consider, of course, two-dimensional situations and such elements given by 1 forms. So in terms of the reduction under a single symmetry, they appear when n is 2. But we can also describe the corresponding multi-reduction under commutative algebras, or maybe under solvable algebras. It's important to note, actually, I forgot about it. It's important to note that sometimes it's possible, in principle, it's possible, there are such examples, when a structure is not invariant under the entire two-dimensional solvable algebra, but is invariant under just one symmetry of this algebra. And the restriction of the other symmetry to the corresponding invariant system has this property that the reduced structure becomes invariant under the second symmetry. So it was not invariant under the second symmetry on the equation epsilon, but it becomes invariant under the second symmetry on the reduced system. And then we can perform the second step of the reduction. So even if our symmetry algebra is two-dimensional and is solvable, we still sometimes can perform the second step, but we need to check that the structure, the geometric structure itself, the structure under reduction, is not invariant under the entire algebra. Yes, let me continue with this reduction of variational principles now. Denote by P epsilon x the projection, the restriction of projection P epsilon to the invariant subsystem, and suppose that one form represents an element of this group. This means that this is just a one form such that its differential is twice Cartan form. And it's important to know that elements of this group are given by representatives modulo just exact one forms. That is by modulo by Derham differentials of functions. The description of this term is especially simple in this case because of the dimensions of the degree. So suppose that rho represents an element of this group, then the rho is twice Cartan form, and let gamma be a mapping such that for every tau, for every first argument, the resulting map is a section. So gamma is just deformation of a section, or in other words, it's a path in sections of E epsilon x. If we have such paths, we can define stationary points of this element represented by rho, and a section sigma is a stationary point of the corresponding element of this group if the formula 61 holds for any embedded compact one-dimensional submanifold M and any path in sections such that its initial value, it starts with sigma, its initial value is sigma, initial section is sigma, and each point of the boundary remains fixed. Of course, when we discuss one-dimensional compact submanifold, they're given by intervals and by circles. So we can describe, we can take, actually we can forget about intervals and describe only everything in terms of circles, then the boundary is trivial. But also we can take segments and describe in terms of segments, and then we require that the boundary must be fixed. This requirement becomes essential in this case. And of course, we assume that each appropriate n is oriented. So this is how we introduce stationary points of elements of this group. And we can do that because elements of this group have this form, just a representative plus exact forms. We don't have here something like plus twice Cartan forms and all of that. So we can consider any sections, not sections that satisfy to some additional requirement, just any sections and any paths in sections in this case, precisely because this is 0. It's important to note that all solutions are stationary points of any element. So all solutions satisfy with this variational principle. We know it for sure. And there may be some other solutions can satisfy with this variational principle. So let's discuss this situation. Denote by 0m the 0 section of this form. Then we get the formula 62. This is just the homotopy formula. The Cartan magic formula or the homotopy formula, we have only one term because we consider a situation when the boundary is fixed, when we vary our section within the class of sections such that the boundary remains fixed. Since the boundary is fixed, we do not have the second term of the homotopy formula. We have only one term here. And it's easy to see that the variational principle in this case is determined by the Duran differential of a representative. And the Duran differential of a representative is just one differential form, right? It's an exact differential form, 2 form. And this exact differential 2 form becomes an element of this group on the first page. So the group on this group on the first page is not the group of elements classes, of equivalence classes of differential forms. Elements of this group are just differential forms, single differential forms. So this Duro becomes an analog of presymplectic structure. The problem is that for epsilon x, we have n equals to 2 or 3 or something like that. So the number of independent variables for epsilon x is not 1. If it were 1, we would have a presymplectic structure for epsilon x given by elements of this form, since they are Duran exact. But anyway, so in this case, variational principles are determined by direct analogs of some classical like presymplectic structures and infinite dimensional presymplectic geometry or symplectic geometry and so on. So in this case, we get just very simple situation, precisely because this is 0. So from like, roughly speaking, elements of this group treat instantaneous states as 0-dimensional. They treat space as 0-dimensional, so space is given by points. And both independent variables, roughly speaking, can be treated as time. It's not a good interpretation, of course. It's just on some intuitive level, it might be a good idea to mention this interpretation. It's not a good interpretation, again. But on some level, it's better to know about it than not to know. And if the rho is a field of operators, I mean, not if, it's important to know that the rho can be interpreted as a field of operators from vertical vectors to Cartan 1 forms. If epsilon x is a finite dimensional smooth manifold, and the field of operators is non-degenerate at each point, then the variational principle yields only solutions to P epsilon x. So the variational principle becomes good in this case. Besides, in this case, the restrictions of the rho or of minus the rho to fibers of the projection of the corresponding bundle are invertible and determine a Poisson bivector. The Poisson bivector maps differentials of constants of x-invariant motion to symmetries, because the local flow of a vector field corresponding to a constant of x-invariant motion preserves the differential form the rho. And hence it preserves the kernel of the rho on epsilon x, that is the Cartan distribution, because in this case, if it is non-degenerate on fibers, the kernel of this form is precisely the Cartan distribution. We can describe the Cartan distribution without the Cartan distribution in this case. We can say that we have these two forms, and its kernel becomes the Cartan distribution in this case. If the field of operators is non-degenerate on vertical vectors. So we have Poisson geometry in this case, something like Poisson geometry. And again, the number of independent variables on this system, epsilon x, is greater than 1, strictly greater than 1. It's like 2 or 3 or something like that in the situations under consideration. But we still have something like Poisson bivector, but this bivector is literally bivector. It is not some sophisticated structure, just literally one single bivector. But it has nice properties, say these properties and so on. Yes, speaking of the invariant reduction, it's important to know that there are algorithms for evolution systems, at least, because without them, it can be difficult to calculate something in this way when it comes to higher symmetries, especially. Consider a system of evolution equations, f equals to 0, where f has components of this form, so we get the system of evolution equations. Then we can say that the algebra of smooth functions on our system epsilon is a subalgebra of the algebra of smooth functions on G's, because we can eliminate all variables that have the form like u, t, and something like that, and all their derivatives. We can eliminate them using the equation themselves. And this is how we can identify our algebra with a subalgebra of the algebra of functions on G's. And the same story holds for forms, for elements on the 0 page, 0 and -1 forms. Let us denote by kappa epsilon the restriction of this kappa pi to the epsilon, and introduce the dense adjoint module. So we introduce kappa pi with hat as the model of homomorphism from kappa to horizontal line forms, and we restrict it to epsilon. Note that phi is the symmetry if and only if we have the formula 66. So usually, like normally on the right-hand side, we must have some total differential operator. But since we deal with a system of evolution equation, we can predict the operator. The operator on the right-hand side, I mean the operator applied to f, this operator. In the evolution case, it can be only the linearization of our characteristic defined in the same way as the linearization of f. Because basically f and phi have the same nature in this case, actually. So f is a section of the same bundle as phi. We can define linearization of phi, not only because of that, but at least in this case, it becomes especially clear. Yeah, an algorithm for conservation laws is based on the following observation. Let x be a symmetry of evolution equation, of evolution system. Suppose omega represents an x-invariant conservation law. Then there exists a characteristic or a cosymmetry and the total differential operator such that we have the following decomposition. We apply dh to omega because omega is a horizontal and -1 form in this case, right? We consider elements of this group horizontal and -1 forms. We interpret them as horizontal and -1 forms, so we can apply the horizontal differential. And on the right-hand side, we have this characteristic part or zero-order differential operator applied to f and non-zero-order operator applied to f. This is how we get an operator A1 of this form. And also we can use the green formula, the Vinogradov green formula, to obtain some other interesting operator, another interesting operator. That is, we just use the green formula for this term and get an operator A2 from this formula. Then we obtain the following relation here under the formula 69. We simply imply the Lie derivative with respect to x, the left-hand side and to the right-hand side, or with respect to the evolutionary field. So the Lie derivative with the evolutionary field commutes with the dh. This is why the left-hand side is given here. On the right-hand side, again, we have the Lie derivative of this term because they commute with dh, and the Lie derivative of this term is given by this term a2f minus a2f because of this formula. So we use this formula just to get this term. And assuming that the Druzhkov homology group of the base M is trivial, one can apply the total homotopy formula to find a potential such that on jets, the formula 70 holds. So we can find a potential of jets using the total homotopy formula. Because on jets, we have this total homotopy formula, and on jets, formulas become simpler. Then restricting this potential to epsilon, we get a desired theta, and restricting this theta to the epsilon x, we get the desired reduction, a representative of the desired reduction, let's say. So now let's consider a couple of examples. I will not use this algorithm in examples. It was just like for information that there is an algorithm or this for the reduction of conservation laws, not only in 1+1 case, but in the general case. In the general case of revolution systems, for revolution systems. Now let's consider the following example: the potential Kalbus-Ines system given by the formula 71 and its presymplectic structure. Here, V is U1, eta denotes U2. We have the corresponding components of the section, F1 and F2. And let's consider the following higher symmetry. We have this higher symmetry given by its characteristic under the formula 72. And let's consider the X-invariant presymplectic structure represented by omega, given under the formula 73. It's important to know that in the case of 1+1 evolution systems, the term, the dt component of a representative is not important for our mechanism. Actually, we can forget about it. Like roughly speaking, we can throw this temporal part of our consideration away. We can get rid of it. And we can, the entire reduction is defined only by this term, by the spatial part of the presymplectic structure. So the presymplectic structure is generated by the Lagrangian for the potential Kalbus-Ines system. It's important to note that the Lagrangian is degenerate in the sense that it reproduces not the equations themselves, but their differential consequences only. And it's easy to see that in this temporal part of the presymplectic structure, we do not have something like theta1, theta2. We have theta1 derivative, right? X derivative of the theta1. So we can see that, roughly speaking, this temporal part is degenerate in some sense. It can be formulated in a rigorous way. Why this structure automatically means that our presymplectic structure is degenerate in this case, but I just don't want to go deep into such details. So let's agree that the presymplectic structure is degenerate in some reasonable sense, because the Lagrangian reproduces not the equations themselves, but their differential consequences. So applying integration by parts, we find to the dx component. We find that in terms of dx component, the following relation holds, but there is only one solution for the equation in terms of dx component, and this solution solves the entire equation of this form, not only for dx component. So we can only care about dx component and solve the resulting part, the part of this equation for dx component, and we can do it integrating by parts. So integration by parts gives us this potential. This potential is not unique, but still, I mean, or maybe it's even unique, I don't remember. Anyway, we can just care about dx component. And the system epsilon x describing invariant solutions is given by the infinite prolongation of the original system, plus two equations expressing the idea that the characteristic must be zero, right? So we just take the characteristic and equate it to zero. Finally, the reduction has the form 77. And this reduction is just one, is a single differential form, single differential two form, as it was supposed to be. In principle, this theta tilde denotes the restrictions of theta of these basis Cartan forms to the equation, to the system for invariant solutions. Yeah, and at first, let us demonstrate how the Noether theorem for invariant solutions works. So let's take the symmetry Y, the shift symmetry, shift with respect to spatial coordinate X. We contract the symmetry with the reduction with this form. And it turns out that we get an exact differential one form. That is, this form is just the differential of some function, the Ram differential of some function. This automatically means that the function is a constant of X-invariant motion, or in other words, for any solution, any invariant solution of the original system with connected domain, this function becomes constant. The restriction of this function on the solution becomes constant. It's a real number on a solution. So it's just like a first integral, the direct analog of first integral. But the system epsilon x is not an ODE system, right? I mean, its Cartan distribution has two-dimensional planes on every point, not one-dimensional. So it's not an ODE, but we still have the same constants of invariant motion. We can use the same things, use them for the same things to integrate the system and so on. But at first, let me say a couple of words on presymplectic reduction. As coordinates on epsilon x, we can take these coordinates because all other variables can be eliminated through equations of the system epsilon x. And in these coordinates, we have this form, right? This reduction. And it's easy to see that there are no v and eta themselves in this form at all. So all the forms contain derivatives only. And all equations here contain only derivatives, and the system itself contains only derivatives. There are no v and eta in this system. This means that there are no v and eta in these differential forms. And we can take the corresponding quotient by the group action, because we have the symmetries, shifts with respect to v and eta. We can take the corresponding group action, but actually it's not important that they are symmetries. We always can take the quotient by the kernel of such form. And this quotient is always a differential covering. Maybe it's not a quotient with respect to a symmetry, but it's a quotient with respect to a pseudo-symmetry, like Vladimir Sokolov's pseudo-symmetry. And in this case, we have a symmetry. We take the quotient, and the quotient is given by the projection. So we just simply forget about reconstruct orbits of this group action. We forget about v and eta because they are parameters on orbits. We get 6 coordinates only, and fibers for the quotient system are 4-dimensional. So we need 4 integrability structures, like 4 conservation laws and 4 symmetries or something like that to integrate the quotient system. And let me note that the reduction 80, this form, is the lift of the closed to form that has the same expression in terms of these coordinates on the quotient system. But the form on the quotient system, the corresponding form of the quotient system, is non-degenerate in fibers. So the quotient system is Liouville integrable. This form is non-degenerate in fibers of the quotient system bundle given in the formula 82. Then we get the corresponding Poisson bivector. Then we get Liouville integrability inherited from epsilon via these 2 symmetries, dx and dt. So the Liouville integrability is inherited from the original system via the invariant reduction mechanism, using these symmetries dx and dt for the quotient system, not for the original system for invariant solutions, right? So we get this degenerate presymplectic form, 2 form, but then we always can perform the presymplectic quotient. I mean, maybe there are some problems with its global definition of the presymplectic quotient, but at least locally we can do it. So we get this Liouville integrability, and now we see that the Liouville integrability is in essence inherited from the original system, from the NLS itself, or from the potential Kalb-Boussinesq itself, via the invariant reduction mechanism. But, yeah, and the last example is the nonlinear Schrödinger equation and its variational principle. Let me demonstrate how the reduction of variational principles works. That is the reduction of internal Lagrangians, because they are variational principles in terms of the intrinsic geometry, pre-formulated in terms of the intrinsic geometry. So we have this nonlinear Schrödinger equation. U and V are real part and the imaginary part of the wave function, respectively. U1 is U, U2 is V. Then let's admit the Noether symmetry X, the higher symmetry, 3rd order symmetry given under the formula 84. The Lagrangian, we have also the Lagrangian for the NLS, written in these terms, in the real terminology, roughly speaking, not in the complex terminology. The Lagrangian gives rise to the presymplectic structure represented by this form, omega. And in this case, we can see that the form is non-degenerate. Again, it's loosely speaking, we can see that it's degenerate, but we can also formalize this, this statement. So we take these coordinates as coordinates on the invariant subsystem. Then we can solve the corresponding equation because the presymplectic structure is invariant, and the invariance of presymplectic structures and conservation laws can be established using their characteristics or presymplectic operators. So it's not that hard to do usually when we know that our equation has trivial topology, the equation epsilon. course, because everything actually happens on the equation epsilon. The reduction is given in terms of the equation epsilon. If it has trivial topology, then we can establish the triviality of the derivative in terms of the corresponding characteristics of presymplectic operators and so on. So we find this solution for our equation, a potential, and the reduction of the presymplectic structure is given by the corresponding restriction. But we are interested in the variational principle, and we have the relation between, in this case, like 1 + 1 case, precisely in 1 + 1 case, we have this nice relation because we know that the restriction is a single differential form, and the internal Lagrangian is any potential for it, but taken with minus. Again, the same minus as in theorem 1 and 2. But it's okay, we can live with this minus. So it's an exact to form. It is necessarily closed form, and exact in this case necessarily exact because it is the presymplectic structure itself was produced by an internal Lagrangian. So there is a reduction in the internal Lagrangian, and they must be related in this way. So it is necessarily exact. And for instance, one can take this potential as rho as a representative for the reduction of the internal Lagrangian. Let sigma be a section of our bundle for the invariant subsystem. Any section, any smooth section of this form, it is given by 6 functions, right? Because fibers are 6-dimensional. So we have 6 functions here, functions of t and x. They are smooth functions, and choose a compact submanifold N1. It suffices to consider pairs of the form 89 that is linear in tau, pairs that are linear in tau, right? For variational, for the variation we don't need anything except linear paths. Delta AI and delta BI are just smooth functions on our real plane, and they're arbitrary functions that vanish on the boundary. Again, we can forget about segments. We can consider only circles in this case. Then we can forget about the requirement about the boundary, but still we can consider segments as well. And in the general case, when it's not 1 + 1 system, we have to keep the requirement on the boundary, because when it comes to, like, say, 2-dimensional compact submanifolds, they cannot be described in this simple form. Or maybe it can be generalized, but whatever. So the reduced variational principle. What is the reduced variational principle? It is given by this integral. We know that stationary points make the integral 0 for any pairs in sections, right? But on the right-hand side, this is again the homotopy formula, just written in a different way, but the same homotopy formula, provided that we know that on the boundary the variation is trivial, right? The homotopy and the variation are closely related. Roughly speaking, homotopy and variation are mostly the same things. It's not a good statement again, but on some intuitive level, they're the same. Here, W is the corresponding field of variation, roughly speaking, can be taken in this form. Not just can be taken, it appears in this form, but on the image of our section. But we can prolong this vector field in the same way on the entire system epsilon x, and then contract. I mean, the formula remains the same without prolongation, with or without this prolongation, in the same, given by the same formula. The relation 90 really remains the same, so maybe it's convenient just to say that it's prolonged, but it's not important. So now at any point of epsilon x, this vector field vanishes if and only if its vector is 0, right? So we can use it just to establish the non-degeneracy. We don't need to use precisely this vector field, but in this case, we can use the same vector field to establish that the form is non-degenerate on fibers. Or we can just consider the form itself without any variation fields and establish its non-degeneracy. So the form defined the field of non-degenerate operators from vertical vectors to Cartan forms. Hence, a section is the stationary point of the reduction of the internal Lagrangian, if and only if it is an invariant solution of the NLS. So in this case, the presymplectic structure was non-degenerate, and the variational principle works perfectly in this case, right? We can see it. When in terms of Liouville integrability, we can consider minus d rho, or d rho itself. Let's take minus d rho that is the presymplectic structure, and we can invert it and get the corresponding Poisson bivector, which maps constant differentials of constants of invariant motion to symmetries, right? Or we can consider the dual story about presymplectic structure itself and symmetries, and the NLS admits the four-dimensional commutative Lie algebra given by the symmetry, third-order symmetry itself, third-order symmetry under consideration, 2 shifts and 1 rotation. So this Lie algebra is commutative. This means that the epsilon x inherits the symmetries y1, y2, and y3, and they give rise to the mutually Poisson commuting constants of x-invariant motion, I1, I2, and I3, respectively. So these constants of invariant motion are independent. That is why one can say that epsilon x is Liouville integrable in the classical sense, despite the fact that epsilon x is not an ODE. We have 2 independent variables, x and t, for epsilon x, and still it is Liouville integrable in the classical sense, right? Yeah, I'm going to finish very soon. Yeah, and the integrability is inherited from the NLS via the invariant reduction mechanism, right? What if a bundle of the form by epsilon x is non-trivial? Because for the NLS, the bundle is trivial, and we can give the following interpretation of this Liouville integrability. We can consider I1 and I2, and we see that Poisson brackets with them become the following derivations, become the following vector fields. And we can say, because of that, we can say, because they describe all total derivatives, we can say that a function that doesn't depend on t and x is a constant of invariant motion if and only if it commutes with both of them. So I1 and I2 can be interpreted as Hamiltonians of 2 commuting vector fields that together reproduce epsilon x. But this interpretation is not invariant, actually. This interpretation is not invariant because we have to choose something like good coordinates. We have to find some appropriate total derivatives. And the difference itself, how to write the difference itself, it's important to note something about this difference in principle. But so the interpretation is not invariant and plays no significant role in the integrability. We don't need this interpretation when it comes to integrability of epsilon x. Moreover, if a bundle of the form is non-trivial, the corresponding system cannot be restored from a fiber using vector fields of the form 93, because this is what usually happens in, say, in Hamiltonian mechanics. We consider phase space given by the equation itself. But the equation is a bundle over real line over time. And we can take the fibers, and the fibers are given by cotangent bundles of some, say, of some manifold, of some configuration manifold. The fibers are cotangent bundles. And then we say that, okay, we can take Hamiltonian vector fields on a fiber, and restore the bundle itself, because the bundle is trivial in principle. We restore it in the following way. We say that we have this Hamiltonian vector field on the cotangent bundle. We introduce a parameter, a formal parameter that describes the flow along the flow of the vector field, and this parameter becomes our base for the bundle, but the bundle can be only trivial. So this means that if pi epsilon x is not trivial, we cannot use this interpretation in principle. So this interpretation is not just non-invariant. It doesn't exist if the bundle is non-trivial in principle from the very beginning. The triviality is essential for the interpretation in terms of Hamiltonians, but not for the invariant reduction mechanism, which is global, and it is given on epsilon. So the idea is that this simple interpretation, it's non-covariant interpretation, but whatever. And the reduction mechanism is covariant, actually, the mechanism itself. But the interpretation survives only when we have trivial bundle structure. If the bundle structure is not trivial, we cannot use this interpretation, because this is how we restore the bundle P epsilon x itself, right? We take a fiber, we take these vector fields, and we say, okay, let's introduce some formal parameters along their flows. Let's introduce a variable x along the flow of this vector field and a variable t along the flow of this vector field. Then t and x become real space and they're base for our bundle, but the bundle is trivial, is necessarily trivial in this case. This means that if the bundle is not trivial, we cannot reproduce the system epsilon x from this interpretation. So this interpretation cannot be generalized to this case. I think that maybe this is an important observation. So here I have some references on this story. This is our paper with Alexei on the archive. Besides the paper by Anderson and Fels with their reduction mechanism, the book General Theory, the paper with the general theorem on internal Lagrangians and variation principles, and some other reduction mechanism. I didn't mention it, but it's also a nice mechanism. I mean, we generalize it on some level, but anyway. Yeah, thank you.
Thank you, Kostya. Very interesting and very nicely presented. Questions, remarks?
I have a suggestion.
Yes, please.
So you consider presymplectic structures, and
Right.
you could consider more general Poisson structures, which are not necessarily presymplectic. And yes, then the Poisson, if your initial equation is two-line, then you have an invariant construction for Poisson bracket as some conservation law on cotangent covering. But after reduction, this cotangent covering will be something unknown, because the equation will be not two-line anymore, and what is cotangent covering of non-two-line equation, nobody knows. But maybe considering this problem, you can understand what is cotangent covering in this case.
Wow, thank you. It's actually very interesting. So basically, you mean that for L-normal equations, there is a description for Poisson brackets in terms of the intrinsic geometry, right? Without
Yes.
any embeddings into jets.
Yes.
Because the reduction mechanism works on epsilon. And it's very interesting. Yeah, I didn't know about this interpretation, to be honest. Yeah, thank you. It's very interesting question.
Thank you, Alec. More questions? Okay, thank you very much. So we meet in a week, next Wednesday, and there will be talk by Valentin Lechagin. I suspect that it will be very interesting. So thank you again, and goodbye.
Thank you. Thank you very much, and goodbye.